So we're going to take a look at the notes, and then we're going to take a look at the assignments together. So this week we're going to talk a little bit more about the TCP IP model. You are going to get asked these questions on Network Plus. So there are two main models that normally are referred to. So we talked about the OSI model a few weeks ago. And this is another model that is parallel with the OSI model. And what you see is you're going to see that TCP IP model groups some of the layers into fewer layers, so it's easier to remember. Some people in the industry, they prefer to use the TCP IP model because it is just easier to remember. But some people, they prefer to use the OSI layers. So we'll talk about the TCP IP model. So I give you a picture and you can look at the relevant protocol, and we'll dive a little deeper into these, right? You've seen some of these before. Okay, so the textbook that I referenced for your notes use a 4-layer model. You sometimes see TCP IP represented with 3 layers. That's less common, but you often see that it's either 3 or 4 layers. So for the 4 layers in TCP IP model, you would start with network interface. So what you see with OSI layers, your physical, your data link, and your network were the first 3. So in TCP, they combine the network interface, which is your physical, and the data link that allows you to have the first layer. So the first layer for the TCP IP model is called the network interface, and that would include your physical cable or network adapter, and also the linking, which is when signal is passed. And when you look at data link, it's really a way to get the structure for the data and prepare it for the next layer. So linking signal on the device. So it really represents the combined first 2 layer from the OSI.
First 2 layers?
Yeah. So if you look at that, right, they combined it for the layer 1 in the TCP IP model. The network and internet, which is what we see with layer 3 in OSI, that's mostly used for IP addressing and routing. And it is basically responsible for the delivery and the connection that is established. Slightly a little bit different. So what you see is it is routing, it is with IP addressing, right? So we're gonna see the source and the destination. We did a little bit of Wireshark last time. You see that in the layer 3, but it sometimes is referred to as internet or network for layer 2 in TCP. And then your 3rd layer is going to be your transport layer. This is specifically for connection-oriented protocol, right? Like TCP, HTTP under TCP, you have that 4-way communication where you have acknowledgement, synchronization, ACK and sync, and then FIN, right? So it is responsible for connection-oriented communication. It also combined the session, right? Which is what you see with transport and presentation in the OSI model. And then for the connection-less communication, where session is not established, it is also under transport. So in the case of UDP, right, it just opens as it arrives, and whenever it arrives, there's no confirmation. So what you see is that falls under the second part, which is where there's not a true session established, right? In connection-oriented protocols, you have to have acknowledgement in how the 2 systems are communicated and agree when and how it's going to exchange information. So transport kind of combined the presentation and the transport in the OSI. That's what you see, right? And also the session. And then lastly, which is parallel to what you see with application layer, the last layer in OSI, it is also the last layer in TCP IP model. And this is responsible for network requests, right, and response. Because it's already established the communication and the agreement. So on the last level, this is when you see the exchange of data and how the data would be represented. For example, in your browser application, you would see that at the application layer. Yes.
Would it be similar to like, they have this new thing on like Android devices where it's like a RCS and SMS that, but. So like, with like, yeah, the part where it's like, you know, just like sitting there, but it hasn't, you don't need for confirmation, it's SMS, but when you do put the confirmations like RCS.
Yeah, it's in a similar concept, right? But with your mobile communication through the mobile network, there still has to be a form of agreement. So it does go through all of these layers. What you see on your text message app is this going backwards, right? So you have to have a connection to receive any kind of confirmation anyway, right? Like, you know how if the message is sending or someone is typing, it's already established your connection to the mobile network and the other individual with that. So.
What if one device, like say it's like on airplane mode, you're not seeing anything?
Right.
And when it comes back on, it's.
Right, so it has to have that connection because, you know, your application function based on that established communication. Yes, you're right. So if I put it on airplane mode or I turn my phone off, right, the sender will not receive any kind of confirmation. Now, the text message, it might be sent through, but it's gonna be stored on the server, right? So once you turn your phone back on, it's then gonna synchronize the data from the server to your smart devices. All your text messages, all the multimedia messages has to be retained at least 3 years on their server. So everything you sent and receive can be retrieved with the court order, right? And I talk about that in forensic class. And then if you store things locally and if you delete it, right, unless it's overwritten on your micro SD or on your internal storage, it goes into a slack space. So if we run recovery software, we can still retrieve your messages and email to most of them, actually, right? Your pictures that you delete. So, yeah, so the encrypted message, you have to get authorization to decrypt that, you know, or you have to have the key. But yeah, they retain your data by law in the United States and North America. It has to be 3 years. Some company does a little bit more, but in other places might be less or more, right?
So when you said about like the encrypted messages, isn't that like when I go in the files in my phone, right? So the files that.
Yeah, so
And then
if you're using WhatsApp or if you're using a type of app that require encrypted message, basically it gives you it generates a key and that conversation is private, right? So if somebody intervenes or trying to read your messages, you know, so it's not in plain text, right? So if someone is scanning you, they won't be able to get your payload and be able to see that information. But if you're using SMS, that's like the most vulnerable type of communication in text messaging. If someone scans you, they likely would see some information about the data, the messages that you're sending across if it's not encrypted, right? Okay, so next we're gonna try to find some protocols that you can refer to the images and the listing on the notes. So we're gonna look at the layers and we're gonna break it down to some protocols that will be relevant to the layers from the first layer to the fourth layer. This is TCP IP model. So Ethernet 802.3, right? That is basically when you connect a cable, an Ethernet cable to your adapter, or when you're using Wi-Fi to communicate, set up your mobile device to communicate with an access point or a wireless router. So you got the standard 802.3 for Ethernet and 802 .11 in that horizon, whether you're using AC or another standard, right, that will be Wi-Fi. Now, those are just some example. You can probably add more. Network and internet, that will be your IP, right? This is where it needs to route, so it needs to have an address. When you're using ping, right, when you type in the ping command in all OSs, right, that is ICMP, and ping also requires established communication, so it would send, and then it wants to receive the response, so that's how we can check if the system is connected or communicating or responding back. You have ARP, address resolution protocol. This allows you to resolve, right, your MAC to your IP address. This is where you would see, so if they are spoofing MAC, they have to modify the MAC table or the ARP table. This allows us to really physically identify that system in the network where it would resolve, like computer A has this MAC address that's correlated with the IP address, right? Why is it here and not at the lower layer is because it uses IP address. So it is a way that it associates IP to MAC address. So it would be able to know what part of the network and which system, right? And then your IGNP. Now for transport, this is specifically for TCP or UDP, right? TCP require an established session or a connection confirmation, whereas UDP doesn't, but it still have to transport from the source to the destination. So connection oriented and connectionless. And then your application, this is what you see with browser, right? HTTP and HTTPS, so port 80, port 443. And then you have Telnet, which is a way that we can use the terminal to directly connect or communicate with the system. For example, I can use my laptop to connect to a switch or a device, right? We can do it both ways. We can use Telnet, which is not secure, or we can use SSH, which has encryption. So you want this form of communication because it would protect how you, like, let's say if I configure a router, I want to connect it with SSH because I don't want people to learn about my configuration for my network. So you would use SSH, and it would require the key, right, from the system that's connected. For both systems actually, so it's gonna generate the key there. And the same way if you are connecting with your Raspberry Pi, right? If you have a laptop and you want to configure your Raspberry Pi, you can use SSH. And then NTP, that's for time. We talked about that in the past, for network time configuration and synchronization. So a lot of these, right, you can actually, these can be server roles like web server, right? This can be remotely for connected, so you can point back to RRAS for remote access. And then it can be a server that sends out information about time on the network on how we can synchronize. Okay, if you go further on the notes, I know that we saw some of this last week, maybe, right? I found out when I was redoing the lab with the Monday group, right? You have to click follow the stream, and then you can actually see the flag that shows up on Wireshark. But if you simply just filter the packets, it doesn't show up the flag. It's just the way the program is designed. If you are using either Real or Snort, it's gonna be slightly different. Right, some of them just shows up with the actual flag when you're looking at the packet streaming through on your capture. Okay, so when you see SYN, that stands for synchronization, This is a flag, think of it like a label that it is assigned to the packets when it goes through the three-way handshake. So after the communication has been established between system A and system B, right? Once they acknowledge that they are communicated, then you have synchronization. This is when data is actually really transmitted. And then the beginning set, which is more on the acknowledgement flag, this is when you can acknowledge that there's communication, and also SYN-ACK actually on Wireshark, that's when it sends and receives the packet that contains data. Okay, so in Wireshark, you're gonna see ACK for communication establishment, SYN for synchronization, and then SYN-ACK, right, is for when it sends and receives data and has that confirmation. You sometimes would see push or PSH. This is when we can force the data on an application. You rarely see that in the regular network environment, but if the system somehow needs to be able to, right, get that data to the application, then it's gonna do a push. That's more rare. And then you have priority flag, like urgent. This is going to be for the systems that needs to send data in a priority format, like, you know how, people pull over for emergency trucks, right, or fire trucks to go through, right? In the sense of the network, when you see this, that's gonna be the priority system that's transmitted. So it's gonna get the urgent. And again, that's gonna be a little bit more rare. You would also see thin. This is when it's finished or it's finalized with the connection before it actually ends. So when you're connecting to a web server, right, and you are trying to access the website, after all of the acknowledgement and the synchronization, let's say that you do a get, which is on get on HTTP, just loads the page, that's what you see, like Google.com. But if you fill out a form online, right, like when you are logging in, typing in some information like to register for an account, that's a set task on HTTP, right? So once you submit that form and the web server transfer that information to the database server, it's going to finish, right? Because there's nothing else that you're gonna do. You submit all of your information, right? It's gonna load that page. Thank you for submitting your registration, right? That's a get. And then after the do a set, then you're gonna see a thin packet coming through where it's finished and there's no additional connection that's needs to be established for that server. But when you saw the connection, I had you write down, right? It would say keep alive, right? That means that you can always be on that website, right? Until you close your browser, then it's gonna end. So when you close your browser, you would see that it would be a thin packet coming through. Yes.
Good afternoon. I always like to discuss.
Okay.
We'll be fine for next week.
There were a bunch of people responded for the one thing.
As long as, whatever.
The five only Paul Ty mentioned, but he thought was an online and I haven't responded to him. Because, I have discipline meeting today, along with UCR meeting today and then at my class. But I'm gonna try to get, so we got coverage for Monday. And so we're gonna probably have to find coverage for two. The harder one is gonna be this afternoon class. Yeah. If all else fails, I can sub next Tuesday. I can sub next
I don't
Tuesday.
want to call my next. I don't want
Like,
to cancel.
I can't be permanent because I'm on curriculum committee, but CIS5 I can do it for a while. I can.
Let's just start in some way.
Okay, yeah, I would prefer someone else doing it. My plate is overflow.
I will. Thank you very much.
Okay,
Have a nice week.
yeah, you too. Sorry. Okay, so, and then your RST is a reset flag where it would be used, right? If the conversation has some kind of error, right? It's like hanging up the phone without saying goodbye, where it terminates early. And the way that they use reset is so that way it can regenerate. And if you ever learn low-level programming, a lot of these flags are actually used. Relevant to how you low-level program for the processor to actually see. Right, all of these network devices, ultimately it has random processors to see these flags. Okay. Any questions? Yeah.
So, you know, how, like, I'm not sure about iPhone, but like for like Android devices, how like say you went to the settings and permissions for an app, there would be like a little option that says force stop.
Yeah,
Which
so that basically stopped the process, right? But force stop, similar to that, right? So if you do a force stop, bless you, if you do a force stop on a packet, let's say it terminates early or something had happened, or let's say that you're being attacked and you need to do something to stop the actual, right, communication, you terminate it or you unplug, right? So when you unplug a cable, when it's already been trying to establish the connection, right, it terminates that. And yeah, it's gonna try to send that flag. Saying that it's not able to reach the destination, something had terminated early, the system is not responding, so you might see some of that.
So which other type of flag would it be?
For the force stop, like if you wanted to terminate, it will probably have a reset at the end. But because before it would have the acknowledgement before you unplug the cable. Yeah, it's gonna try to do a reset. And you're gonna see it coming through with an error. You see like the black packet that you saw in Wireshark last time. So sometimes systems, like it stops the connection somehow, or it lost the connection somehow, then you might have a reset.
It's like, there's been times where I did force stop, right? And it says that, you sure you wanna do this, and then make this, application act up.
Yeah, so ultimately, when you do a force stop, so your app always have processes that are running. So for example, if you have a Google Map app, right? And you turn on your GPS, where it would notify Google where you are all the time. And then you decided that you don't want that app to be actively working, right? You want to disable the app. So you press the force stop button. What that does is it terminates the processes for that app. For example, like the GPS navigation of your phone, where you are in the world. A lot of these apps have microphone enabled, so that way it can listen in on your conversation to obtain your data. And that's part of your terminal agreement. It also track your search pattern and other things, along with like even the text that you type sometimes, right? You gotta be careful. I found out, well, one of my students were telling me that Temu, you heard of the company, they sponsored like NFL last time. Yeah, Temu. So on the app, someone had posted on LinkedIn, a security professional had posted that it actually interrogate your clipboard. You know how when you copy and paste text and things like that. So last year they were saying that the app itself, if you look at the permission, it actually pulls all your whatever that you click, like URL or whatever you copy paste. So there was a lack of security in that area, right? So yeah, in that sense, I originally had Temu and then I eventually uninstalled it because it was, and then you don't know how they store the data and where they store the data. So a lot of these things can be, but again, Brandon, when you force stop, that just terminate the processes for your system, right? It also could be application that would be related to communication, right? Because these apps are always connected. Right, it has to be connected to its server or whatever the website that it is communicating with. Okay, so before we get into this section, let's check back over here. So it gives you all the breakdown and specific protocol, right? Network News Transfer Protocol, which is NNTP. You don't see a lot of this anymore unless they have like, I know RCCD has it for the faculty and the staff, and it uses an old server where It can send out like messages based on updates for the company. And then your flags are here. So before we talked about UDP header, I want you to look at TCP header. Like you saw, right, on Wireshark, the percentage is gonna be like pretty close. A lot of times you're gonna have more UDP packets compared to TCP packets. So these flags actually exist on the actual content of the packet, right, in the header. So the header, think of it like a label for your packet. And the header is where your network sniffer or your Wireshark actually pull the information from to give you what you visibly see on the app. So this is gonna tell it how big is the header, right? And this are just the reserved bits, but these flags actually have its place. And so for each packet, depending on what it's doing, right, what the intention for the packet, then you would have the flags turning on or off. So ultimately at the low level, when we see these are like bits, binary, right? So if it's on, like for example, if it's doing acknowledgement, that bit is actually turned on. And so that's how it's able to see that it is a flag that's set. And then if it's off, if it's 0, right, that flag is not on. And then, so you would have, if it's urgent, then it's gonna use a pointer. So ultimately it is a location where it would have the information for the urgent packet. Your sequence number, remember that it is, the packets is gonna be broken into, or your data is broken into many packets. And with TCP, that it needs to have everything back together, like the bicycle, like I said, right? The handle, and then it's gonna put everything back in order. So it's gonna use the sequence number to be able to organize your data and structure it to how it's, from top to bottom, okay? And then the acknowledgement number comes back to the app here, right? Sorry, the boss. There's someone, oh, sorry, it got locked by accident because it slides back. And then your payload, remember we looked at the payload size? So usually your payload is chunking up into like bytes or megabytes if it's, depending, and we talked about like how if it's like if it's like the super frame or the super larger payload, right? So you will see that there, but it has the data information, like how much data it's carrying. It's kind of like your shipping label. It's going to tell you the weight of your content that you're shipping. Okay, so we saw a lot of these things, right, through Wireshark, and that's like the best way that you can visualize what, your traffic would look like. Now compare that to your UDP header, it is much smaller. Because it doesn't really require a lot of these acknowledgement, a lot of the flags that you see. So it's just like, oh, where it's sending from, where it's going to, how big, and then the checksum parts to make sure that, the entirety is, there. So you would see the difference in the two, in that UDP doesn't have to have a lot of the confirmation. So that way in this header, it's a lot more simple. Okay. Okay, so let's answer that. Okay, so for your UDP header field, you have a source port. This is gonna be 16 bits, okay? And that really tells you, how when you look at the source port for the UDP, right? We talked about like dynamic port compared to well-known port last time. And when you look at those, the source port for DNS, right? My system might be connecting to the DNS and it's using like 65, let's say 65,001, for example. Where the destination port also is a 16-bit. The system, the DNS system, the server, it's actually receiving that at port 53, right? So it would have these port information like doors and windows on how system would use those doors and windows to exchange information, exchange data. And then the length is gonna be 16-bit. It basically specify the size of the header in bytes, right? How big is your header? And these things are really important in ethical hacking and vulnerability assessment for security because you mainly are gonna look at information from headers, right? When you're looking at like attack traffic or, if you're scanning, if you are, trying to look at how far you can push that system, right? If you're doing some kind of pen testing, right? So these little bits and pieces of information, you need to kind of know like what's the component of your header. And then your checksum just to verify that everything has integrity or everything is valid there. So compare that to TCP. TCP has headers much more, right? It has more details, it has more components. So we just need to understand the difference. Now, the crafty, right? If you're looking at pen tester or even the attacker, the crafty people, when they are crafting or they're modifying the packets, right? A lot of this would relate back to the header itself, right? If I'm modifying the payload, which is the data that's contained in that packet, likely that it's going to have to modify the content or whatever that's specified on the header itself, right? So when you're using a tool to craft a packet or modify a packet, usually it would start with modifying the header, and then you can also add context. So there are tools that you can stuff packet, add more data into a packet, and then resend it, right? But with that, it has to modify some of the information that's contained. Just like how if I intercept your package that you're sending to your friend, right? And I'm trying to add more items to the package, well, it changes the weight, which changes the label for the post office to deliver that package. So it's a similar concept. Any question? Okay, and we can find all of this on this section right here, which is page 4. Okay, you can go to the notes to reference that. That's where I put down the information. Okay, let me move 4 down so we can see it on the next page. Okay, so now we're going to talk about IP header. So each of these things have its own header, right? But let's look at the entire component first. So now this is the next layer. This is when you have IP addressing and you're gonna have routing. So IP protocol, it says on the router is using IP, right? That's what it's really designed for, to be able to send, and ultimately, it has a component called time to live. And this TTL is going to prevent it from just looping. And when you have a loop in a network, it consumes your bandwidth, right? Like for example, if you put the wrong label onto your package and you're trying to send it to your friend, right? If it's a wrong address, it doesn't get there. So they just keep trying to find that address, right? Or it's gonna search. So it's gonna come back to your system. It's gonna say, oh, let's try to resend. That's what our system is designed to do. So it creates a network loop. And when you have a lot of these loops, you're gonna have, floods, and then it creates like the slowdown in your network. So what it does is it's gonna decrease to 0, right? And the router is gonna remove that, and it sends the status back using the ICMP, which is like a ping-based type of service. So that's going to, so that's how it's checking to see if that packet actually gets to the right IP address, right? And then in Windows environment, the default is going to be 128 for time to live. So this is the same thing when you're doing a ping, right? So for example, if I'm doing a ping, it's using TCP, but let's say if I ping, for example, an arbitrary address, right? Like, I don't know if that address exists or not. That's an IP address, right? And so if it exists, you would see how it have time to live, right? It has that window of time that way, so that way it can reach the person. It's like how the post office tell you that, you know, the package is gonna deliver your house to your house in 7 days. If you're not home, then it's just gonna get sent back, right? So that time to live is going to be the amount of time that it uses to be able to reach that system. If it reaches the max of that, right, it resets, it decreases that to 0, so it sets that to 0, and it would notify the router that it's not reachable. Okay, so let's try if I have another one, let's say that if I do like 108.1, for example, right? So see how it says it's expired in transit, it's not reachable. So I completely, this packet is not reaching the destination, right? And the system that they use to reply, right? It's not finding that on the network, so it cannot route it. So this is what you see. Okay. Sometimes it just say unresponse, and then you have 100% loss. Okay, so on the IP header, the field that's specified when the packet expires, you saw that on my ping, is time to live, right? Now, if you use ICMP is used for like pinging services, checking system connection status. And there are different applications that it does that, right? So if we use a ping command, that's a type of command that use ICMP service. And so how does it know the different type of messages that is transmitted between the systems, right? It's really the codes and the type of the messages and the way that application or the command is designed to do. Okay. Okay, let's come back here. So if you want to look at IP header, you can look at the image here, the time to live that we talked about here, right? Most header would contain the protocol information, of course, right? And of course, where it's coming from, where it's going to. So IP is a little bit different than your TCP. Again, TCP has additional flags to check for connection or not, right? Most of the header would have checksum to make sure that there's integrity for the packet. And then the fragment offset that's just gonna be the space where it's gonna look at how that's to be scattered. And then the total length of the actual packet. Now, the reason why they put the version pieces there is because you have IPv4 and IPv6. Okay, so it gives you the breakdown of what each component would be. It does contain the smaller flags for the fragment, right? So that will be your DF right here. These are the flags for IP. Okay. Okay, so ICMP information is following that, going from 5 to 6 page. So you saw the ping command, how that works, right? Let's try trace route. So I can do google.com, right? You can simply take the fully qualified domain name and then it, it would be able to, because of DNS, it's able to plug in the IP here for you. So what I want to do with traceroute is I want to follow the traffic from my computer to google.com, right? Like how many routers does it pass through? Now, in Windows environment, it's going to only give you a summary. Now, if only Google allows me to really get the information. So first, we're gonna see that it's leaving my system, and google.com is gonna try to reach the server IP address, right? It's not, because this is the way that DNS works, is to be able to associate that. So because it's google.com, this is the IP address. So it's leaving, right here is the first router that passes through for this particular segment, right? Like, because I'm coming from the wireless side of the network, and it's gonna go through that gateway. Then it's going to get to the district system that's gonna forward that. Then here is where you started to see that it's gonna get to this particular system, and now this is the service provider. So when you see cynic.net, that's gonna be the service provider, right? And then it's gonna pass through a bunch of autonomous systems. And what you would see is when we get to the end, you notice that it's gonna go to the closest server for Google, which is out of LA. Okay, now they might host it in LA or across the country, but it's labeled as LA, right? Because normally they would host it on one side of the coast, and then they would have a secondary failover on the other side of the coast in case if we have earthquake here, another system can pick it up. And this is the cloud environment. So what you do is you're gonna get in between, you're gonna have autonomous router that's gonna get you from point A to point B. And this is how we access the internet, is through service provider and autonomous system, which are routers that, pick up our traffic and forward it, right? Okay. So, and Windows give you the traces. Now, some domains, you cannot trace them, right? They are intended, they shield, so when you trace, it might show timeout because they block that, so that way you cannot follow the traffic on, if it gets there, and then you have to request the information if you want that. So trace route in Windows, you use trace RT and then just the domain name. You can also use the IP address. So I can plug in this IP address here and that works, right? We'll talk about utility next time. But in Linux, you have to spell out trace route, one word, that's entirely trace route. Okay. So that's another form of ICMP, right? You can see that with traceroute and ping. So trace basically follow the traffic from the sender to the receiver. If it exceeds a certain amount of time, then it would also, again, it has a window where it would submit the request. So traceroute actually takes longer, right? It's kind of like, if I'm following you from home to school, right? Every time that you turn on a street, I have to report back to my system saying, oh, this person turns right? This person turns left. So when you do a trace route, it echoes the information back to the requester, to my system. So your traffic actually is taking longer because it has to keep reporting back for every single router that it has. Whereas if you just visit the website, right, it simply is a lot quicker, right? So there's some description for ICMP. And so this is what you see with like the ping where it does the echo reply, right? And this is the code that we're referring to when we answer, okay? So the numerical value really allows us to see on the command line, right, whether it's reachable or not. So the way that Windows command prompt works is it takes this code and interpret it for you when you do that command. So it shows you whether it's reachable or not, right? So ultimately, these are the codes and this is the type, right? So, and the way that they design the terminal or the command line in all cases like Linux, Windows, or even Mac, right? It takes these code and interpret it to text that you can see, verbose information that you can see on the CLI. And then your ICMP header is like this, so the code takes up the bytes, right? And then it does a checksum. It also have a sequence number because ICMP is part of TCP. It also function at the IP level. So it is, it does have that acknowledgement. It is connection oriented. Okay. Okay, so we talked about the code and the types. Any question? And then if you want to read a little bit more about Internet Group Management Protocol, this is going to be working at multi-layer, and it does use multicast, right? It really looks at like how you can use this to be able to manage all your system. We do this for automation in IT. So for like, specific systems or specific group of systems. So I can send, so for example, I'm gonna give you a quick example. Like, how all the computer labs, they have to update software occasionally, right? But we don't want that same software to be for the staff or the faculty. So, the group of systems that can be placed would be, it's gonna do a multicast in the image. So I can create an image with the student software, and then I can send that out to only the segment for the computer lab for the student. And it would do that. It would send it to those groups only, okay? And I can do that for the purpose of convenience because I don't want to manually go into every computer lab and update the software or install the software individually, right? And then if you want to install OS on all the computer, you can do a broadcast, right? But in this case, it's using multicast. Okay, I talked a little bit about ARP. When we looked at ARP later on, we'll probably see a little bit more. So like I said, MAC to IP, right? ARP poisoning is simply changing the ARP table. And remember, your ARP, it caches. So this, if you want to pull the information, usually it's on the RAM of the appliance or the system, right? So you can do an ARP command in command prompt, and you would also be able to see your own system cache information, like which system is connected to IP and MAC address. So someone can get a hold of your ARP table. They can modify your ARP table if it's not protected, right? And then simply store that. And so, for spoofing purposes or other things. Okay, any question regarding these protocols and layers? Like I said, right, technicality sometimes can be difficult because it's new information. Go back, read, and kind of review, try to look at some example. That's also going to help you. Okay, IPv6. We're going to spend a little bit of time looking at hexadecimal today, right? Another number system. So IPv6 was introduced in 2011. They had researched this quite a bit because IPv4 ran out publicly. So IPv6 used 128-bit address. Remember we talked about IPv4? It's only 32-bit. So if you do the probability in the 32, 2 to the power of 32, it's much less than when you do 2 to the power of 128. Right, exponentially, we are much larger in the address space, right? But they're saying because of our IoT devices and all of these websites and all of these things, public IP version 6 will eventually run out. Same thing with MAC address, right? And then we have to use a different system. So, IPv6 is really designed with components that is more automated. Where you can assign actual static address, but it's really designed so that way it can easily be adapted without much like subnetting and all of these things. So it's much bigger and easier to use. Okay, so it uses multicast as a core for the method of IPv6. And then when you're using ICMP with IPv6, you have to have that version, right? So ICMP, it will say ICMP v6, right? Just like how you have IPv6. So there are protocols that are specifically designed with both versions of IP. So just keep that in mind, okay? Okay, so the types of IPv6 addresses, you can just like IPv4, we can use it for one-to-one, which is unicast, one to a group, multicast, and one to everybody, that's anycast. That's like broadcast in IPv6. Remember, we talked about 255 as a broadcast for that host, right? So there are components of IPv6 that is able to meet communication needs from one system, one to a group of systems, and one to all systems. So there are three types of unicast, right? One-to-one. You have a global unicast. This is going to be your public address. Okay, like public IP address for IPv6. And then when you look at the IPv6, and if it says site local unicast, that is a private address that's used within the LAN. And then if you have a linked local unicast, which is very common here, if you're looking at, if you do IP config and you see a lot of networks might have linked local unicast. This is for linking only. So that means that they are using IP version 4 predominantly, and they might just use IPv6 only for linking purposes, right? But in the case, if you see like the global, think about the world, that's public, right? The site local, name says it all, right? That's LAN. And then the link local, that's for linking only. It's really simple. Any question? Yeah.
What do you mean by linking only?
Linking only is to establish the segment system to that segment only. Right? And so when it routes, it's still going to refer to IPv4 to route. So it would get you to the router ultimately, but the router is going to look at your IPv4 address to route. Okay, any question? Now, like I said, right, you would see the version 6. So if you use IPsec, which is used commonly for virtual private network servers, right, or the service that we would connect. If you build like a virtual VPN server, you can use IPsec, which is a recommended protocol, but you would use the version 6. Right, IP version 6, so it will say IPsec version 6 versus the default IPsec that's the version 4. Okay, so let's break down the hexadecimal. So today you're gonna learn a little bit more about the hexadecimal. So I give you an example here, right? This is what you would see some IPv6. That's what it looks like. It looks kind of like the MAC address, but much longer, right? You are going to have hexadecimal numbers. So you're going to have 0 through 9 and A through F. Okay. Whenever you see F, that's usually, it is a broadcast address, right? So when you see the 0 in between here, that can be concatenated. That means that we don't have to type out a bunch of 0 in the middle. The system also sometimes condense that into like a double colon and a 0 to represent like there's 2 chunks of 0 here, right? So you would see some concatenation, and it talks about that here. So I could take this portion and indicate it as a double colon to saying that these bits are not on, it's off, right? So you would see some condensed value like this, right? And so instead of writing out a bunch of 0 like this, we can shorthand it. And you see that in some system, it would represent that. So instead of writing it like the entire, how many 0 you have to type out, right? you simply just indicate it with a double colon and the 1. That just represents all the 0 following it. And then some system, it would show you like this, right? It concatenated like the 4 hex value here, which is gonna be represented with 1 0 in the front. And then the ultimate value that we care about is this last one. It is of significance, right? Because everything else is off before that. Okay, so the types, we talked about that here. So I want to touch back on this a little bit. When you're looking at an IPv address, we talked about this last time, right? A IPv address is really an address that is used by the OS for a placeholder for that system. It's not a network address, it's just an address that will eventually be replaced by a real address. In IPv6, you're gonna see it's indicated something like this, an FE80. Okay, so when you see that, you know that it's not a network, a private address that's usable yet, right? It automatically was there, right, for communication with the nodes, but it's not part of your LAN. And then your link local, if you use a site local unicast, I'm sorry, a site local unicast, it would start with an FEC0, something like that. Commonly you would see. Okay, so here is the table, right? So your decimal value 0 through 9 is equivalent to a hex value 0 through 9. So when I say a 0 in hex, that's a 0 in decimal. And that's also a 0 in binary. But when it's after 9, when we count to 10, 10 is going to be equivalent to the letter A, right? And if you do the 10 conversion, right, you're going to have the 2 and the 8. 2 plus 8 is going to be 10, so it's 1 0 1 0, right? And then 11 is equal to B. 12 is equal to C. 13 is D, 14 is E, and 15 is F, and the system stops after that. There's only 16 number in hexadecimal, 0 through 9 and A through F. All right. So the easiest way to do the conversion from hexadecimal to decimal is to go through binary, right? So for each character of a hex, that is represented in 4 bits, which is a nibble. And every hex character, it's gonna take up 4 bits. So if you're looking at the value F, right, that's a hexadecimal with the base 16. How do I know it's all 1? So F is 15 in decimal, right? And if you look at the table, 1, 2, 4, 8, right? We don't care about the rest because we only care about the first 4 bits. Remember the scale from last week? Okay, we only worry about half of a byte. So multiple of 2. 1, 2, 4, 8 is your decimal equivalent. And we want to take 15 and we can subtract. So 15 minus 8, you have 7 left, right? 7 minus 4, you have 3 left. 3 minus 2, you have 1 left. And 2 minus 1 minus 1, you get 0 left. So when you get an F, all your bits are on. Okay? That's at the end. So this is like 255, right? Remember we talked about 255. So when it broadcasts, you see that it's at F because all the bits are on. Okay? Any question? Okay. So now let's go through and answer the next question. Okay, so I try to color code it for you. So you're gonna start with the number 2. Okay. Remember, 2 in hex is 2 in decimal. If we have the same table, 1, 2, 4, 8, then what we would have is which bits is on at 2? Well, the 2, right? And everything gets 0 because we convert 2. So you take the 2, you subtract whichever that's on the scale, which is 2. That's the highest I can subtract, right? The 4 and the 8 gets a 0, the 2, because we subtracted, we place a 1. And there's nothing left, so it turns off on the last bit. So your value for the 2 in binary is going to be 0, 0, 1, 0. Right? Everybody follow so far? So you take the 2 in hexadecimal and you convert it to the binary because 2 is equivalent to a decimal. You use the same scale. Then you take the next digit, which is a 6. Right? Same scale. So you ask yourself, which number adds up to be 6? 6 in hex is 6 in decimal. Of course, the 2 and the 4 is going to be 6. And the 8 is off and the 1 is off. Okay. So hexadecimal conversion to binary is actually really, really easy. Okay. I don't bother showing you the division process. We just do the subtraction. That's good. Okay, so, and the scale we're going to have is going to be 1, 2, 4, 8 every single time. And then, of course, the 0 is going to be 0. All of the bits are off. 0, 0, 0. So that's our next digit right here. Then you move to the next one, which is the 3. So the 3, I know 2 plus 1 is going to give me a 3. So the first and the second bits are off. Okay. And you can go through and do the subtraction just like how you did decimal to binary. We do hexadecimal to binary. We use the scale and we subtract. Now it gets a little harder when you get a letter, right? You just got to refer to the table to represent the letter. Now you can also plug it into your programmer calculator and you can check, okay? So I don't need you to show all the work like a math class. The whole point in this demonstration to show you this particular exercise is how it gets converted. So to sum it up, when you convert that's hexadecimal to binary, you know that there are 4 bits. So your scale is going to be the decimal equivalent is going to start from 1, multiple of 2, and it's only going to go until 8, right? And when you just go down the list and you subtract based on that scale, right? The value that you can subtract and place a 1 underneath, just like how you did with the decimal version. Okay. And then after that, you're going to group all the binary values together and you have your answer. Okay. All right, let's try the letter A here, or the F. We already talked about the F, where all the bits are on, right? Because that's 15. The letter A is 10, okay? So A in hexadecimal, which is a base 16, we are going to be, it's equivalent to a 10 of a base 10. So our decimal is 10, then that's a letter A. So if you look at the scale, what number adds up to be 10? The 8 and the 2, right? So it's 1, 0, 1, 0. So 11, 8, 2, and 1. So it's 1, 0, 1, 1. So if you go down each letter, it's going to increment by 1. So it's just going to add a bit as it goes, right? So 12, what adds up to be 12? 8 and 4. So 1, 1, 0, 0. And so on, right? So if I look at the next one right here, FA40, right? That will be 111 for the F. The A is 1010, right? And the 4 is easy. We already solved that. So the 4, it's going to be 0100. And the last digit is 0, then it's off. Everything is off. 000. Let me change this font to white so it's easier to see. Okay. So if I look at the letter D, right? So A is 10, B is 11, right? 12 is C, 13 is D, right? So 13, what adds up to be 13? 8, 4, and 1, right? So this on, off, and on. Okay, well, that's why we designed a programming calculator, right? So you don't have to manually do this, but I want to show you how you can do it. So the easiest way to convert is to group it, each of your hexadecimal value is 4 bits, right? And then use your decimal equivalent scale. You can go down and do the subtraction for the bits that are on. Then if we can subtract, we place a 1 underneath, just like how you did the decimal. Okay, so that's kind of, you can practice. Okay, so I did the FA0 here so you can see. FA40. Okay, so now we need to do the reverse. We're gonna place the binary onto the table like what we did with the decimal. But now we have to look at the hexadecimal, right? So you're given, for number 10, you're given this binary value. And the way that I write it, I like to chunk it up into 4 bits because that way I can distinguish from one hex character to the next. Oh, sorry. I meant to change that to white. Okay. So the first one, which is all ones, we already solved that from the last. When you see all ones, you know it's a 15, and that's an F, right? So you put all the ones together, that's an F. So 8 plus 4 plus 2 plus 1 gives you 15, base 10, which is F base 16. Okay, so that's the first one here. And I color code that in yellow so you can see. Then you have the 1101. So that means that the 8, the 4 is on. So 8 plus 4. And then the last bit is on. That gives us 13. So that's equal to the D as in David. Right? The 8, the 4, right? 0 is up here, and then the plus 1. So I have 8 plus 4 plus 1 gives me 13. So the green here, this nibble equals to a D. And then I would go to the next group of bits. So 1001. So the 8 plus the 1 gives you a 9. And a 9 is a 9 in hexadecimal. And then the last nibble, which is 1011. And so 1, right? The 8, we skip the 4 because the 0 there. We're going to add the 2 for the next one and the last one. So 8 plus 2 plus 1 equals 11. So you use the same scale you put the binary value on the bottom of it. And whichever the bits is on, you add it, right? Just like how you did binary to decimal last week. So this entire binary value represents FD9B, right? Why is this B? Because it's 11 and anything after 10 is a letter for hex. So 10 is A and 11 is B. So you have FD9B. And when you look at the binary now, if you know the scale, you can put the number. If you use the scratch paper, you can put this little small number on the bottom. That's what I normally do, and I can add it up. Right, so when you look at this, you already know that the 8 is on, so 8. This is 2 plus 4, so that's 6, right? 2 plus 8, that's a 10, which is 8. And then this one is a 1 plus a 2, that's a 3. It's much quicker once you get into the pattern of it. Okay, and if you want, you can put the scale, the table, you can handwrite it out. And how do I check my answer? I can open up my calculator. I talked about this last time. Go to programmer mode. And then you can take the binary, copy it. Go back to your calculator, click on bin, right? And then on here, I think you can paste. Oh, it doesn't let me, but you have to probably type it in. And you can check. So I can go into reverse and check my answer, right? I can do FD9B, and I can click the binary to make sure it matches. And it matched. So the answer for A is correct. And then same thing, you punch in hexadecimal, you just select hex. And then we can put in for question B, 86A3, right? It's gonna give you the matching binary. So you know that it is. So when we do binary to hexadecimal, similar to decimal, you're gonna add up the value for the bits that are on, right, on that scale, and the sum or the total, when you add that up, that's gonna be the hex equivalent. And anything after A or after 10, right, to 15, we have to convert it to a letter. And this is the easiest technique that you can do hex conversion. There are some techniques that involves multiplication and division, right? So you have to do long division, you might have learned that long ago, right? And then you have to do multiplication to go in reverse, but I found that it's a little bit more tedious and you tend to make more error if you don't divide things and keep your remainder correctly. So the takeaway in this, break it up into a nibble or 4 bits for each hex character, right? Subtraction when you go from hex to binary, and addition when you go in reverse. When you go from binary to hex. But for C, I didn't solve that, so you can use your calculator or you can do it yourself then. All right, now we're going to talk about octal. I want to make sure that when you see these values, you know what they are and how they're used. Okay, so octal has only 3 bits, right? Octal is used in older 8-bit systems, right? You ever play really old games, right? Those are smaller bit size, like, you know, those, I don't know, old Mario games or whatever. right? Those are the smaller bit size type of console systems. So octal been around for a long time, and this is a base 8 number, so that's only gonna be 0 to 7. Okay? And so the 0 in octal is the 0 in decimal, and 0 to 7 is the same. So you only care about 3 bits. Okay? So if we take the octal value 24, we can't say 24 because it's not a decimal number. 24 in octal, we need to convert it into binary. Similar to what you did with the decimal and the hexadecimal, you use the same scale, but only for 3 bits. So 1, 2, 4, and it stops there, right? So you take the 2, you ask yourself, right, which one can I subtract? Okay, or let's start with the 4 so you don't get confused. Let's take the 4. Based on the scale, which one can I subtract? I know that I can subtract the 4, put a 1 there, and the rest is a 0. So the 4 here is going to be 1, 0, 0. Right? Just like how you did the decimal, but we only worry about 3 bits versus 8 bits, right? Like before. And then the 2 on the scale, which one is on? 1, 2, 4, 8. I mean 1, 2, 4. The 2 is on, so 0, 1, 0. So same technique. Okay. So the 2 is 0, 1, 0, and the 4 is 1, 0, 0. Now your calculator is able to do octal. Okay. So let's clear this. If I click OCT, I can put in 2 and 4, and then I get a binary. Oh, I mistyped this. Oh, yeah. Okay. So this is confusing because the calculator, right? You see how this is? It's designed to give you a byte. Okay. The way that you can change this is this size right here, right? So the double quad word actually represents 64-bit. So what you can do is you can modify that to kind of shrink down, but technically, right, it's only going to be this and this. You see that? It puts the 0 in the front. Some of my students, they get confused when they look at that, right? So your answer is correct. It's just it adds the 2, 0 in the front because it's really designed to give you like a byte. Okay? All right. So if you want a word, right, which is a word is 16-bit and a byte is 8. So it's just going to try to shrink it down, but by condensing it. Okay, so you can try, okay, I think I saw for B. So you take a 6, that's going to be 1, 1, 0 because it's 2, right? Plus 4, because there's only 1, 2, 4. 2 plus 4 is going to give us a 6. So that's 1, 1, 0. And then the 2 here is on, so 0, 1, 0. We solve it in the last one, and then the 1 is 0, 0, 1. Any question? So if you're able to do binary to decimal, then you should be able to do binary to octal or hexadecimal, same scale. Right? Octal only have 0 to 7, hexadecimal 0 through 9, and A through F. How often are you gonna see octal? Not too often. Only on older, if you have older appliances, you might see the number. Any question? Okay, So now if we go in reverse, if you take the binary value, right? Let's move this down. If you do number 12, you use the same scale and now you do the addition. So if I have 1, 0, 0, because I highlighted in dark. So if I do 1, 0, 0, so 0 is, it's off on 1, it's off on 2, it's on at 4. So you have a 4, right? It's on for the second octal, you're gonna get, it's on at 1, right? So I'll type it out here. So 4 is, it's 100 is equal to base 2 is equal to, right? 4 because it's 4 plus 0 plus 0. Oops. Okay. Now, if you go to the next one, which is 10101, and that's a base 2. You're going to take the 4 plus the 0 plus a 1, which gives you a 5, right? In octal, and so on. You get the idea. I might as well do the last one. 001 in binary is going to be equal to, right? You take a 0 plus a 0 plus a 1, which gives you a 1 in octal. Any questions? Yeah.
How do you format the boxes like that?
The scale here?
Yeah.
I simply just add a table. So if you go insert, table, and I want, because there's only like 3 bits, so I want 4 columns, right? And 3. So you can specify 4 columns and then 3 rows. And it automatically scale if you have it on auto here. And there you go. Right? So again, just insert your table and then you specify on how you want it. And then this scale is always going to be 1, 2, 4 because it's multiple of 2 for binary. And I put the bit position, so first bit, second bit, third bit. And then the binary is when you plug it in. So if you have the last assignment, you can copy and paste, but only with like the 3 bits instead of the 8 bits. Okay, so we can practice. B should be 276 in octal. And then C you have to solve. Okay, we're almost there, just a little more, and then we'll do the lab. Okay, so now what we're gonna do is we're gonna look at the IPv6 address, and you have to put down, right, how it would be concatenated or how we can write it in an easier way to see, right? Like I mentioned before, anytime that you see a lot of zeros like this, we can condense it to an easier, shorter address, okay? So the first thing, what we're gonna do is we are going to look at the first 0 after 2026, okay, we can omit that 0 in green. Okay, you see that right there? The 0 that's in the front of the value, like in front of the F, in front of the A, in front of the C, because that bit is off, we don't care about that. So you can just ignore it. But you have to keep the value that is significant. The C, the B, and the O. Okay. We can omit the 0, but we gotta make sure that the C, B, and 0 that's following gets placed underneath. The next group of zeros, because they are 0, we can condense it to a double colon. Okay, because these are a bunch of zeros, so when you see a double colon, that would represent that there are 0 in the middle. Okay, and then again, FC0, because there's a 0 in the front, you see how I highlighted in green, right? We can omit that green 0 and we have to keep the FC0 in the subsequent value, which is this right here. We bring it down. Now you can use a double colon here for these guys, or you can just, another way that you can write it is 0 and condense those 4 bits to 1 0, right? So I can make it a double colon, or I can just put :0 for each 4 bits. You understand? Or each 4 digits, I should say. And then on the last one, because it has a 0 in the front, I omit that and I bring down the A to E. Okay, so there's 2 ways that you can write it. You can write it this way, actually 3, right? You can write it with a double colon and then the 0 for the middle part right here, that's our 0. Or you can write it with the colon and the 0, or you can write it with double colon in for both parts. So I can say 2026, right? CB0, and then we would do a double colon, and then bless you. And then we do a FC0, and then a double colon, and then A to E, like that. So either way is correct. So the takeaway from this is anytime that you have the 0 in, that's in the middle, or even, in the middle. So if you have 4 digits that are 0, you can condense it to a colon or a :0. And then if you have a starting value 0, you can omit it from the actual address when you write it. The reason why I show you this is some system shows it like this. Okay, some software, it will come up like this, and you have to know what they mean. Okay, this is not just because I want to give you busy work, it's because you have to know how to interpret this to a full address. Okay, so if a full address is like this, we can have it condensed or shorthanded in 3 ways. So it depends on the software designer or the developer or the system engineer, how they want to represent the value for the full address. Any question? Just remember that full address is going to give you 128-bit. So if you see it short like this, of course it's condensed, right? If it's shorter than 128-bit when it's written out, it's condensed. Okay, any question? Okay, so I put a link for you to read more about IPv6 address representation. Okay, so now we're going to look at the prefixes. So when you pull up an IP address v6 version, you might see a /4, right? In IPv4, we call this a CIDR, a CIDR. But this prefix really represents, similar to a CIDR, the bit size of the address. Okay, you know how you have the 255, right? That's indicating your bit subnet mask. In IPv6, same thing, right? What you need to know is always know that you have 128 bit in IPv6. That's where you start. When you have a /4 like this, you're gonna take 128 bit, you subtract the 4 that's indicated here, and you would have 124 bits for the number of hosts that you have. So if we put this into an exponent, we will be able to calculate out how many hosts. So this is the number of systems I can connect on that subnet, basically. Okay, so the way that we subnet in IPv6 is to use the prefix. Okay, and that prefix represents the number of bits that you borrow. So you would take 128, you subtract that prefix value, you have 124. Then you plug it into the exponent with the base 2, and you can use your calculator with the scientific mode to be able to calculate this, right? So if I take 2 to the power of 124, I would have this many hosts. Many hosts. So that means that there is an indirect relationship with the prefix based on the number of hosts. So if this number is lower, I would have a higher exponent. Understand? So that means that if I have a higher exponent, I would have more hosts. So for B, same thing. I would take the prefix, which is 24, and I know that there is 128 bit in the IPv6 address. So I would take 128 minus 24, which gives me 104. And I would put that I make it an exponent of a base 2. Why base 2? Because the computer, it uses binary, 0 and 1s. So you would take 2 and put it to the power of 104, and you would have the number of hosts for that subnet or that segment. So as you can see, when you increase the prefix number, right, you have decrease in the host value. So there is an indirect relationship with those values. Same thing with 64 here, right? If you have a prefix of 64, I simply would be able to yield that by saying I take 128, I subtract 64, which gives me 64. Oh, I meant 64 and I typed 65. And then I plug that into the exponent, which is the n value. So when you subtract, you get the n value, and you plug that value for the exponent, which gives you the number of hosts for that segment. And that's how you do it. Pretty straightforward. So when we get to subnet for IPv4 later, you're gonna be like, it's kind of similar. We're still gonna use a base 2, but so the takeaway from this, to summarize this, right? Start with 128 bits, which is the address size for IPv6. Take the prefix value and subtract it from 128, which is a full address size. The remainder, what you left, is going to be your n value or your exponent for a base 2, which gives you the number of hosts that you can have for that segment that's represented with the prefix. Question? Not too difficult, right? And then you can use your calculator just to do the math. So if you work with, network engineers, or if you function as a network engineer, you're gonna have to determine like how many system you need, and that's gonna be able to help you lead to the number of the prefix value that you're gonna use, and how do you calculate that, right? You already know how, right? Okay, for 15. So how does a computer generate its own IPv6 address without using the same IPv6 address of another computer network? You know that there should never be the same IP address on the network. If you do, you are gonna have miscommunication or disruption. IP version 4 or IP version 6. When they designed IP version 6, they had this in mind because administrator and technician would put in the same IP address by accident, version 4, and that creates conflict or disruption. So the way that they create the network adapter for IPv6, they have an auto configuration process on the adapter where it self-generate the IP address by checking existing IP address that is version 6 for the nearby systems. Okay, so before it creates that IP address or generated, it looks at, or it has the IP address and it's going to compare it, right? So when it does the neighbor solicitation, it's kind of like, you're in the room and you ask the other person, like, what's your name? What's your name? Right? Because you cannot have the same name as another person in the room. So before you create your own name, you check to see who's in the room and making sure that their names are unique and your name is unique. Okay? So that's how it does it. And if the system is already using the address, the other systems, right, the neighbor system is going to say, hey, I already have this address and you cannot have this address. So it makes sure that it is not identical, okay, to the other system. And so the other system will respond to it, right, to tell it not to use other addresses. And that's how it works. The reason why I wrote this question is I think even sometimes when you read through the concept, right, it might not be clear. It's easy to understand, and it's just a form of solicitation. It's just checking to see what the other systems have and making sure that it has a unique address that's different from the other system. Any question? So there's a lot of heavy lifting with already taken care of with IPv6, I believe. Like configuring, dynamically assigning IP addresses. Yes, you can force it into a certain scope or whatever, but the network adapter has already been designed to do this because we thought about the challenges that we had in IPv4, and the researcher and the engineer that designed IPv6, they already knew what the problems that we have. And so going into IPv6, in my opinion, IPv6 is a lot easier to administer compared to IPv4, but traditionally you see IPv4 everywhere because the network's still working, right? We're not going to tear it down and reconfigure or use a different number system. We slowly transition to it, and 15 years later, we're still transitioning. Okay. Yeah, 2011, if you look at that up until today, right? It's 2025, right? Going into 2026, we're ending at 2025. So yeah, 15 years in. Okay. Let me move this down. So we can answer the rest. Okay, so in IGMP, and you heard about Internet Group Messaging Protocol, or Management Protocol, I should say. It is really focused on multicast, right? The protocol that replaced IGMP in IPv4 is what's called the MLD, which is your multicast listener discovery. This was, the intention for the protocol was to be able to target specific group of systems, right, by sending it the information, could be instructions or information or data. So the replacement from version 4 into version 6. So when you look at version 6, it would be multicast listener discovery instead. They did transition it to where it would be the same protocol with a different version, only because I think that there's a huge improvement from the version 4 into the listener and discovery. Okay, so you saw traceroute already, right? You saw how the automated system, the routers, right? A lot of them are just, it tells, it's kind of like, I'm standing in the neighborhood and I tell all my neighbors that, hey, I'm free, I can help you, right? And so you would have various systems that communicate that way. So there would be like open shortest path first, we'll talk about routing later. But there are protocols that are specifically used for IP version 6 for the routers to determine whether it is endpoints or it is a network system. So when I say endpoints, remember how we looked at that on Wireshark? Those are systems that are connected to the network, but no further system connected from it, right? So they are exactly the name, endpoints. So for example, if you have a tablet and you connect it to your wireless router and nothing else is connecting to your tablet, then that system becomes an endpoint. But if you have an iPhone that you connect it to the network, but you use it for tethering, right? So other devices can connect to it, it is no longer becoming an endpoint, right? Because now it has its own subnetwork within. So what you see is that they have these tunneling protocols. So the reason why we use tunneling protocol is we implement encryption. That allows you to encapsulate it so that way the communication between the devices are protected. We do this for VPN purposes, for secure communication purposes, but there are specific protocols that the routers use to create this tunnel. Just envision that if you drive under the tunnel, the helicopter cannot see you. It's exactly that, right? The name really represents that it's encapsulated in a way where even if you strip the header, it is harder to see the content of what the communication would be. So there would be specific protocol that's used for this, 624, Burrito, and Torito. It's designed for routing purposes. Okay. Okay, so let's go through and talk about the services again. Because this is going to be related to your communication systems, your servers are running the services, and it's important to know them. So when you're sharing files, printers between Windows and Linux systems, you use a service called Samba. This has been around for many, many years and it's still being used. So let's say that I work for a company that have Windows systems and Linux servers. A lot of time web servers run Linux servers because of licenses, right? So if you have a lot of systems that are requesting your service, you're not having to pay licenses. You tend to see less Windows IIS, where you would see Apache or NGINX for web server, the majority of them are. So it uses Samba. So that means that I have to install it, right, to be able to use it. Okay. Next, resolve convert NetBIOS name for IP address. We talked about this last week. WINS, WINS, names to IP. Translate private to public IP address. This is your network address translation net. You see this on your virtual machine, and your home router does this, your wireless router. You only have one public IP address, right? But you might have 10 devices in your network. All of those 10 devices use that same public IP address. And the service that makes it happen, NAT. So it exists in every single network. Okay. All right. Plan, document, manage all IP subnet. That's known as IPAM. So it's just a service that we would use to manage our subnetworks that are IP. Remotely connect to Windows network to access files and application. The keyword here is Windows and remote. So that will be remote desktop protocol, your RDP. This is used for cloud connections when you are at home and it's 2 a.m. and someone tells you that that segment is down and you need to connect to your network to reconfigure that switch. If you're using Windows, you're going to use RDP. Securely. Right? Or you can SSH in once you connect, you have a public IP address, but. Okay, so minimize configuration of clients by broadcasting services on the network to the clients. You can use zero config. This is a form of configuration where if you are setting services for many systems so this gives us automation, right? So when you broadcast, you send to all clients that are connected. Sometimes there's a need. In enterprise network, we do a lot of multicast and broadcasts for automation purposes, for infrastructure management. Question. Okay. So, we're gonna take a break after I take attendance and stop recording. You are going to copy the server, just like how you did the Windows VM last time, to your desktop. It's on these drives, right? And you are going to use the ones on your desktop to configure. I'll walk you through on how to create a DHCP server, and create a scope for your server. So we want to make sure that you know how to do that leaving this class. So that's something you can be adding to your resume, right? Configure Windows server. Now, if you use in 2019 compared to 2022, which is the latest one, not a huge difference. I just happen to have the image that's 2019. You can practice on 2022. It's like 2021, 2022. If you want, most companies still use the older version before they upgrade, because when you upgrade, you gotta bring down your server, reinstall all of the services after you install the OS, which is not always ideal, right? So when Microsoft push a new version, it doesn't necessarily mean most companies will wait like a few years before they come. So, all right. And then let's stop. Let me